everybody. And we have today extraordinary seminar because our dean is able to change Tuesday into Friday. But thanks to this, we can listen to the talk of Piotr Chruściel. So Piotr, you are welcome.
Yes, good morning, everyone. It's a pleasure to give a talk again in this seminar. I haven't been there for a while, probably more than a year now. So I didn't have anything interesting new to say, but I like this new result. So I thought I would try to share it with you. So this is based on work with Erwann and Raphaela, and it's on archive for the last few weeks. And this is about this theorem, which is not in preparation, but it's already actually on archive. There exist three-dimensional, conformally compact, asymptotically locally hyperbolic Riemannian manifolds with scalar curvature equal -6, with connected conformal boundary at infinity and with arbitrarily high genus and with negative total mass. Okay, so this is a very long statement. So let me just try to unravel it step by step. Well, the main point here is negative total mass. Well, asymptotically locally hyperbolic means that the metric approaches a hyperbolic metric at large distances, right? So you go away at large distances and you're approaching a hyperbolic metric. This is about initial data sets in general relativity, not about space-times. So in dimension 3 is asymptotically locally hyperbolic is the same as asymptotically Birmingham-Kotler, and I'm going to remind you what it is. I imagine most of the people here know what Birmingham-Kotler metrics are, but in any case, I will present them again. Now, conformally compact here, by this we mean that there is no interior boundary. So in other words, you have a manifold which has no event horizons. Yes?
There is some interaction of microphones. I don't know what to do. Wojtek, you know what is the reason for this?
Maybe some people should turn off their microphones.
Yeah.
Because I don't think mine is picking up echo or anything like that.
No, it doesn't seem any have microphones. So
okay, so
I don't know.
Well, let me know if there's a problem, but I'm not aware of any. I don't hear anything untoward in my headset. That's right. So conformally compact means in this case that the manifolds, when you use a Penrose type completion of your manifold, you get a compact manifold without boundary. There's only a boundary at infinity, but there are no interior boundaries. Now, negative total mass was known with black hole boundaries, or if you had two infinities, right? So if you have say static metric with a black hole, and then you can double the manifold across the black hole, like you have in the Chruściel solution. You have this Einstein-Rosen bridge. You can always do this. And then if you have a black hole with negative mass and the solution is static, you can just obtain a solution with two boundaries by doubling, and there is no interior boundary. But so in this case, there's no such option, right? There's no interior boundaries. Now, this condition R of G is equal -6 is telling you that if you think in terms of energy in general relativity, then you have an initial data set with a negative cosmological constant and without matter, right? So this is a vacuum initial data without matter, time symmetric. So there is no extrinsic curvature tensor, time symmetric general relativistic initial data and the cosmological constant is actually monomized to -3 here. Now, these solutions have arbitrarily high genus at infinity. So such solutions were known with a toroidal boundary or quotients of sphere, but not with higher genus. This is three-dimensional, and I have no idea how to generalize our construction to higher dimensions. So this uses really very strongly the fact that the boundary manifold is two-dimensional, and on a two-dimensional manifold you have the uniformization theorem, which tells you that every metric is can be just well, the only information is the scalar curvature, and locally it's conformally flat, and we're using this all the time. Good. Why do we care about this theorem? Well, first of all, asymptotically hyperbolic manifolds are all over the place in theoretical physics, so in supergravity, in string theory, in holography. There's CFT-ADS. These kind of manifolds show up all the time. Even if you don't care about the supergravity, string theory, holography, CFT-ADS, but just think about plain vanilla Einstein equations, classical, then you have space-like hypersurfaces in solutions of Einstein equations with or without cosmological constant lambda, which are just asymptotically hyperbolic. So in anti-de Sitter space-time, if you take the standard static slices t equals 0, then the metric on it is exactly hyperbolic space. In Minkowski space-time, you can take a hyperboloid, and the metric on a hyperboloid in Minkowski space-time is exactly hyperbolic space. So even if you don't care about these other fancy theories, just they occur naturally in natural classes of solutions of Einstein equations. And this is an interesting mathematical problem anyway, so that's good enough for me as a justification. Good. So I promised I'm going to remind you what these Kotler-Bernal metrics are. So these are static solutions of Einstein equations with a negative cosmological constant. The metric has a simple form. So there's this lapse function which has a specific form given by this formula. The important thing is asymptotics R square in this part of the metric and in this part of the metric. Then this metric HK here is so as you see that, well, of course, nothing depends upon time. And this metric HK does not depend upon R and time either. So it's just a metric in the other variables. And if you assume that this metric is an Einstein metric, so Einstein metric means that the Ricci tensor is proportional to the metric, then and you take this manifold to be compact, and in fact you don't have to, but it's usually one does this assumption to have a well-defined mass. So if you take this manifold to be compact, n-1 dimensional, this is in all dimensions, and the scalar curvature of this metric HK is constant. So this depends upon the dimension. Would be what would be probably 2 in n equals 3, and the sign this k is in 0, 1, or -1 is the thing which determines so the sign of the scalar curvature of the metric HK determines what sign you have to take here. And I'm going to assume that n is larger than equals to 3, so that I don't have to discuss this case n equal 2, which is different. You notice that with n equal 2, this is a constant, so it's hard to unravel what is the mass and what is this k. And anyway, and in any case, this R of h is 0 here. Now, the point of this mass things is that when you have a metric like that, you can define the mass of the metric G is a parameter m, with a background metric, which you take to be the same metric, but with a parameter, mass parameter 0. And then there is a procedure to define mass, which tells you when you do this, then the mass of this metric is actually proportional to this parameter m. Well, if you have an m which is non-zero, then you're going to get a singularity unless.
Excuse me, I have a question. What means relative mass?
Well, what is the ADM mass? The ADM mass is the mass of a metric relative to the Minkowski metric, right? It's nothing more than that. So you can define ADM mass because you set up asymptotic conditions, and the mass is defined with respect to the asymptotic background. And so here it's the same, right? So you have a background metric, you say, which you take to be the mass parameter 0 here. So this term will be gone. And you define the mass of a metric which asymptotes to this one. So here in this case, it's a very specific metric, but then you have a lot of metrics which have this asymptotics. And then you can define a mass, right? Like in a asymptotic flat case. You do this.
Okay.
Okay, so if m is non-zero, then you're going to get a naked singularity here, unless this function has a positive 0, right? So if Vm square, which it looks like the notation, it should be positive, but note that it doesn't have to, because the way it appears in the metric, it's always squared. Now, if this function has a positive 0, then you get a black hole. If it doesn't, then you get a naked singularity if m is non-zero. And yes, so asymptotically locally hyperbolic is something that that people use in various theories. Well, actually, is the same as practically BK in 3 dimensions. So this is really what you're interested in. And but in higher dimensions, actually, you can have locally asymptotic hyperbolic metrics which have a more general asymptotics than this, right? So that's something which is irrelevant for this talk, but this is, well, would be relevant if one wants to understand how to generalize what we're doing here. Good. So this is Kotler Birmingham, or Birmingham Kotler. Kotler was a colleague in Vienna, well, a few years back, actually some 100 years back. And he wrote probably this metric for k = 1 and in 3 dimensions, but or maybe k = -1, I don't remember now. So Birmingham generalized to this class of the metrics, which I just showed you. Now, another important metric in this context is the Horowitz-Myers instantons, and you get this by something which is called weak rotation, right? So just take Birmingham Kotler metric, and you change the sign. The minus here becomes a plus, and you assume that this boundary metric, which I had here, HK, is flat. So you write it in flat coordinates. And you change one of the coordinates on the flat boundary, you change the sign here, right? So this is called weak rotation. And whatever this means, if you can just check that the Einstein equations are still satisfied. So this is a static solution of vacuum Einstein equations with negative cosmological constant. You assume that this boundary metric is flat, so kappa is 0 here. And now if this is a Riemannian metric now, right? So here a 0 of Vm was a killing horizon. Now in this case, this becomes a smooth axis of rotation, a 0 of Vm. And of course, if m is positive, this metric will always, this function will always have a positive 0. Then the only thing which happens is that you have to make sure that the periodicity of this angle here, so this is an axis of rotation, and this is an angle along this axis of rotation, and the periodicity of this angle is determined by m, right? So fixing m fixes the periodicity. Right. And so what else can I say? I think I already told you this. It's called core geodesics, this axis of rotation in n equal 3. And of course, if you change m, it means that you have to change the period, which means that the metric at infinity is not the same if you change various masses, right? Because you have a circle component at infinity, but the periodicity or the length of this component changes, right? So you can change m, there's nothing wrong with that, but this changes the conformal class of the metric at infinity, right? So this has to be keep in mind, and which is not the case for the Birmingham Kochler matrix, right? So these m and conformal class infinity are completely independent. Now, the main point of this matrix is that, well, first, they're conformally compact, so there is no interior boundary, and the mass is actually proportional to the negative of m. Previously, the mass was proportional to m. Here, it's proportional to the negative of m. Well, you have to do the calculation, and so these metrics have negative mass. There's a conjecture by Horowitz-Myers that these are minima of energy at prescribed conformal structure at infinity, right? So you can have, once you have such a metric, you can produce immediately using the conformal methods or other methods a lot of solutions of the constraint equations with these asymptotics, and then you can evolve them. You get a nice space-time, which is negative cosmological constant. Each of them will have maybe a different mass. And because these guys have negative mass, then there'll be a lot of solutions which are non-trivial with negative mass. And the conjecture is that if you prescribe the conformal structure at infinity, then these provide a minimum for the mass, right? And then remember that this parameter m is actually related to this conformal structure. So the mass for this matrix can be arbitrarily negative, right? Because you can just take this m to be arbitrarily negative. But at fixed conformal structure at infinity, then you should have a lower bound. Okay? I mean, at fixed conformal structure at infinity, you have exactly one parameter in this metric, and this should give you a lower bound for such metrics. So I've proved with some colleagues some partial results about this conjecture, but this is wide open. I mean, there's no theorem about it. And I just wanted to show you how well, how much more complicated the question of mass and its sign is when you are in the asymptotically hyperbolic case. In the positive, in the asymptotic flat case, well, you have the positive energy theorem, right? So the mass is the energy momentum vector is future pointing time-like, and that's it, right? And so there's no options. Now here, if you look at the class of asymptotically decay metrics, because you have these various topologies at infinity, there are a lot of cases which occur. So the simplest case is that when the topology at infinity is a sphere and a sphere at infinity, you can still have many metrics in higher dimensions. In dimension 3, you have a two-dimensional sphere, and up to a conformal factor, there's only one metric. And because here, this whole geometry is kind of conformal, what really matters is conformal classes of metrics at infinity. So in 3+1 dimensions in space-time, so two-dimensional boundaries of initial data set, you can have a canonical. If you assume that the topology is spherical, you only have this case, canonical spherical. And we have a positive energy theorem here. So there's nothing surprising happening here. But you can have other cases, right? So you can have this Ricci flat conformal infinity. And so an example is the Horowitz-Myers matrix. And here there are two cases. There is a case which I call good spin. And in this case, you have a positive energy theorem. And there are cases which are not good spin, and of course they exist because the Horowitz-Myers exist. And if you don't have an interior boundary, so no black hole, then this is the Horowitz-Myers conjecture here, that the mass is larger than a critical mass. And if you have a boundary, then well, this is not clear, right? So if you have a boundary, whether you can have negative mass, I think that with the methods we are using in this paper, we can probably prove that you could have solutions with negative mass and a black hole and a toroidal, but infinity. But I don't want to make a too strong a claim because I think we know how to try to do this, but it's well, we haven't finished the details. So let me just explain you what is this good spin structure. So proving one way of proving positivity of theorem uses the Wutte method, and the Wutte method consists of solving a spinor equation with specific asymptotic conditions. So first, to solve a spinor equation, you have to have a spin structure. So if you don't have a spin structure, you cannot even do this. And in high dimensions, a lot of manifolds don't have a spin structure, so forget it, you can't do anything. But say in 3 dimensions, you always have a spin structure. So 3-dimensional manifolds are always spin. This is a nice theorem of Garage. So, but being spin is not good enough, because when you're trying to prove the positive energy theorem, you have to solve the Wutte equation with boundary conditions, and the boundary conditions are tailored so that you can read off the mass at infinity from some integral. And so if you don't have spinors which give you these boundary conditions that you need, then you are dead. And so you can have, if you take a standard Kotler-Birmingham metric, which is toroidal, then the manifold is a product, and you have good spinors there. And then you can and this theorem applies, and it gives you these positivity theorems. But you have a Horowitz-Myers metric. It is spin because it's 3-dimensional, but it does not have good spinors, because if it had, the solutions would have positive mass, but they don't, right? So that's one way of proving that you don't. But otherwise, you can just try by hand to look at the spin structures and see that doesn't work. Now, this is canonical spherical. This is Ricci flat. There are other conformal infinities. So in Clarkson and Mann produced an example in 4+1 dimensions, which has a spherical, well, a quotient of a sphere, so a length space at infinity, which has negative mass. And in this higher genus case, in 3+1 dimensions, this was not known until our work, right? So our work is actually filling this window here, and 0 being the archive preprint that I'm talking about. So higher genus in 3+1, this is the example that we construct here. And so let me mention that there exist some other, so when you have a boundary, then you can of course have negative mass for the Birmingham-Kotler metrics with higher genus. And there is a nice theorem to which I will return at the end of this talk, which says that if some condition on the asymptotic behavior of the metric is satisfied, then the mass is larger than a critical value, which is negative. And otherwise, it's not known. And in fact, our work shows that this condition here, that of our friends Dunley and and Andre Neves. Actually, there exist solutions which violate this condition and also violate their inequality here. Good. So that's the setting. And how do we do this? The idea to produce. So the remainder of this talk is actually to explain you how we produce higher genus solutions with negative mass. And the idea is to use gluing at infinity, and goes back to a theorem by Jim Eisenberg, Jack Lee, and Iga Stravrov, 2010, so about 12 years ago. So you take two asymptotically hyperbolic manifolds with constant scalar curvature, or you can also do it with initial data sets more generally, and you can construct, so given two such sets, so here are your sets with a conformal boundary at infinity. You can construct a new one by making a connected sum at the conformal boundary at infinity, right? So you just glue these things together by gluing at infinity, right? So this is the theorem, and we showed with Erwann that you can actually localize this solution by doing Carlotto-Schön type gluing, which means that in their construction of Jim and friends, you're making a conformal transformation of your manifold, which is global. In our case, we only make a deformation of the metric, which is located in this small region where the gluing takes place. And so, well, you see this result and you think, okay, there's something called energy momentum in general relativity. So what happens with this energy momentum when you do this? And the obvious first reaction is, well, what could happen here? They would just add period, right? So that's the obvious first reaction, and that's not exactly what's happening, but essentially that's what's happening, right? So you can think of our construction as saying, well, you take two Horowitz-Myers solutions, so they have a negative mass, you put them together, the masses add, and you get a negative mass at the end. That was our first idea 3 years ago already when we started thinking about this, but it turned out to be a little more complicated than this. So what is the energy momentum of the initial data set? I think that for this audience, just defining mass is bread and butter. So I can only regret that if you look at the literature, then people tell you, well, we use the methods of Wald to define mass, and Wald developed his framework in 1990. And here in Warsaw, we know very well that actually the way to do it goes back to Kijowski-Tulczyjew, 1979. And yeah, it's a sad fact of life that just people don't seem to be aware or to understand this method of Kijowski-Tulczyjew, and they keep quoting Wald. Now, whether you're using the Wald formalism or the Kijowski-Tulczyjew formalism, when you have a metric which approaches a Kotler-Birmingham metric, then there is a nice formula for mass, which is this one. So you might be more used to formulas for mass, which are pretty ugly with partial derivatives of the metric or something like that. Here, everything is kind of nice and geometric. So this is Rij, the Ricci tensor of the space metric, right? So it's not the space-time metric, which in vacuum it would be zero, but it is a space metric. Or it's its trace. So this is the trace-free part of the Ricci tensor. So obviously this is geometric. What isn't completely geometric is that you're introducing a function v here, which is nothing but the lapse function for the Kotler-Birmingham metrics. So this depends upon your background, right? So you have a metric which just asymptotes to a Birmingham-Kotler metric. You put in this static potential or the lapse function or whatever you call it, or the static kid in there, and that's the formula for your mass. And there's a coefficient which depends upon the dimension, which is irrelevant. Good. So let me come back to this theorem which we proved with Erwann some 7 years ago. So you take two, and let's just think about the Horowitz-Myers situation. So you have a torus at infinity. So your Horowitz-Myers matrix sits inside. This is the boundary at infinity. Normally, this would be nice and round. And but what we did with Erwann, we showed that you can replace this. That whenever you have a general relativistic initial data set or constant scalar curvature manifold, you can cut off a little bit piece here and put hyperbolic, exactly hyperbolic metric there. So we take two such Horowitz-Myers metrics, we glue them together, we get a Bretzel, right? So a manifold of genus 2. And more precisely, so think of this as being your torus, and you take a small coordinate neighborhood at the boundary. So this is your boundary. Then you have if you go inside this torus, so now here we are inside the manifold. Then there are two regions. The red one, so you start with whatever metric you had here, with, say, constant scalar curvature. You produce a new metric which still has constant scalar curvature. And in this red region, the metric is going to be replaced by the metric which is exactly hyperbolic. So no matter what metric you had here, which is asymptotically hyperbolic or asymptotically locally hyperbolic, you replace the metric with one in this region, which is exactly hyperbolic. There you have an intermediate region where something happens, so where you need to somehow connect these things. And outside of the blue region, you have exactly the same metric as you started with, right? So except inside this half ball, this is a half ball, and boundary is a plane, so this is a half ball. The metric is outside the metric is what you started with, and inside the red one, it's hyperbolic space. Now, there is a weird property of hyperbolic space that if you take a half ball in this representation here, then its boundary is a totally geodesic submanifold. And totally geodesic submanifolds have the property that when you have something which has a totally geodesic manifold in one boundary in one manifold, something which is totally geodesic boundary in another manifold, then if you put them together, well, if the metrics match, then the metric will be actually extend C1 across this. And in fact, when you do this inside a little inside the hyperbolic region, then will it match smoothly, right? So if you touch together these two donuts with a bit cut off, and the cutting off is done at the boundary of this region, then what you get at the end is a smooth manifold, and obviously it's again asymptotically locally hyperbolic and all this. So now there's something interesting which happens here. Well, when you're defining the mass on each of these donuts, then you're using a flat as a BK metric, Birmingham-Kotler metric, which is a flat boundary at infinity. So we call this toroidal BK metric. Now, once you've done the gluing, of course, there's no flat metric in the conformal boundary anymore. So when you want to define the mass here, you need to use a metric which is negatively curved now, right? So you have a genus 2 at the boundary metric, which has constant scalar curvature equal -2, where you started with 0. So the initial mass was defined with respect to one BK metric. The final one was defined with another one, right? So the initial toroidal background was this one. If you go, if I went back to my to my slide about Birmingham-Kotler metrics, then you'll see that this is what it is. The one which is negatively curved will look like that, and you need to understand what happens with the mass. And here the point is that this metric here, which is the in local coordinates hyperbolic metric of constant scalar curvature -2 or sectional curvatures -1 on each half, this metric is conformal to this one, right? Globally, you can't do this because there are no flat metrics on a bretzel. But on each half, you can write such a conformal factor. So on each half, you have a conformal factor here. As I already said, initial mass defined with respect to different backgrounds. And so you just make a calculation and check that the new coordinates R bar is going to be e2 minus omega 2 R times R by lower order terms, right? So in other words, when you're doing this conformal rescaling of your boundary metric, you need to adjust your coordinate, and that's the formula for this. So it's, I mean, essentially obvious from this if you compare these two metrics, but that's what it is. And there are lower order terms which you need to include to make this formally self-consistent. And then in the original mass was defined using this formula, where the lapse function was equal to R. Now in the new manifold, the lapse function is square root R square minus 1. So the lapse function appears in the space part of the metric as the square of the lapse function is this factor, right? So this is the new one. And if you just put this expansion R bar into this formula, then at the limit, you can ignore this -1 term, and you get this simple formula for how the mass changes, right? So if you make this conformal change, then the initial mass is calculated like that, and well, the new mass is calculated like that, and this is on each half, right? So on each half, so if you do this gluing symmetrically, as was suggested by my picture, then the mass of the new manifold will be twice this this expression. So this is our theorem, right? So which tells you how the mass changes. So we have two backgrounds, one with one constant kappa, the other one with a constant kappa bar. The initial mass was this. The new one is this, right? So and this works for we used the kappa equals 0 and kappa bar equal -1 before, but this works quite generally. Now here, there's a question mark, right? Because can the metric be asymptotic to two backgrounds globally? Well, in some cases it can. In some cases it cannot. So, for example, if you glue together two spheres, the new manifold will again be a sphere, and therefore you can have globally this representation formula. And this is something we used in a previous work to prove positive energy theorem with a spherical boundary. Now, if you are on a torus, obviously you can't, just for topological reason. However, and this is an example on the torus where you can have such a situation if you take something which is called a punctured torus. A punctured torus is a torus where you put a hyperbolic metric on it. And however, of course, for topological reason, you cannot make it smoothly, but you can take a conformal factor which blows up at one point. And the result is a geometry which looks like that. So this region, this is actually an infinitely long neck, which is thinner and thinner, right? So this is a finite finite version of this, but this actually goes all the way to infinity, right? So think of this as a very long needle, and which, of course, if you look at a curve around here, then it becomes thinner and thinner. So you can have a hyperbolic metric on a torus, not quite on a torus, but a punctured torus, and then this formulae would probably apply. Well, with a little grain of salt, one has to be careful, because then the metric at infinity is not compact anymore, right? So you have to remove this point, and so these formulae, understood as they stand here, for a metric which has a singularity and infinity, I don't want to interpret them too literally, but we're going to use this puncture metric. It's going to actually play an important role in what follows, in a limiting sense, right? So we'll be never using a singular metric at infinity, but we'll have to, actually, this metric will turn out to play an important role in our argument. So the mass of each half is now given by, we do it symmetrically. So we have the mass contribution is the same from each part, and this is the mass of each part of the manifold. So we have this conformal factor here, and this conformal factor depends upon epsilon, right? What is epsilon? The epsilon is the radius of this circle here. It looks like it's a constant width, but you can make it smaller and smaller. So then this connecting region will become thinner and thinner. And the mass of each half depends upon epsilon, because omega depends on epsilon. And now there's an important thing which I should have mentioned before, and I haven't emphasized, that when you try to do this mass kit gluing, so that you put in hyperbolic space, then in this region, then, well, I've already told you that there is a deformation area where things are a deformation. So if you just took with if we start with a Horowitz-Myers metric here, then there will be a region near this gluing where the metric is not Horowitz-Myers, it's changed, right? And the way it's changed, well, there's a perturbation. The perturbation is small, but so that when you go with the radius here to 0, the mass of the new manifold will converge to the original one. So if you started with Horowitz-Myers, you get a perturbation here, which might make the mass of the perturbed thing positive. So you have to take this epsilon small enough so that the contribution of the perturbation near the gluing boundary is smaller than your initial mass, to make sure that you had something negative, right? So you have to control pretty well what's happening with this conformal factor here, and to check what is the influence of this factor on the mass in the region which is not exactly hyperbolic. In the region which is exactly hyperbolic, you don't care, because this is 0. But there is a region where you care, and then you need really to know very well what's happening with this factor here. So you need epsilon small, and you need epsilon as small as possible. And so the standard way of solving problems like that in mathematics, and well, that's the only one we could figure out after thinking about for 3 years, and eventually it worked, is that well, you first press to the limit of with epsilon going to 0 and see what happens, right? So the theorem is then when you make a mass kit gluing of 2 Horowitz-Myers metrics, then this conformal factor, and let me just remind you that this is right. So if you've already forgotten here, so this is the flat metric, this is the negatively curved metric, and e to omega is the conformal factor between them. Then when you mass kit glue 2 Horowitz-Myers metrics with parameter m, then this conformal factor, which happens for every step when you do the gluing and you tend with epsilon to 0, it tends to the conformal factor of a punctured torus. So what's happening here, that you have this bretzel, the neck becomes thinner and thinner, and when you pass to infinity, these things separate, right? Here it looks like they're still connected because epsilon is non-zero, very small, but when you pass to infinity, then this each of these ends becomes infinitely long, and these things are become two distinct manifolds, right? So the manifold separates in two in the limit epsilon equals 0, but before it's still connected. And the theorem is then the mass of that you get when you do this with epsilon to 0 tends to this number. Right? So this tends to this number. Now, of course, and so when you take epsilon small enough, this integral is strictly positive. Obviously, mass was positive, so the number would be negative. And that's the construction of our solutions. Let me.
Can I ask a question?
Yes.
So how this omega looks at this puncture of the torus?
It's 1 over. So if r is the two-dimensional distance from the center, it's 1 over r log r square.
Ah, okay, thank you.
So so e to omega, right? E to omega is 1 over r log r square. So omega would be log of all this. Now we sweated quite a bit on this theorem. It took us a lot of time to prove this, and it probably follows from some results in theory of hyperbolic manifolds, either by Volpert or something called the Deligne-Mumford compactification of the Teichmüller space, because this is what it is about, right? The Teichmüller space is a way of parameterizing the metrics on a bretzel, for example, and I think that maybe if you understood well enough what these guys are doing, you could just quote them rather than doing all the work we're doing. But so we tried very hard to read this result in a form we need from their papers, and we couldn't. So we just had to reprove it by hand, and in any case, that's the result you get. And so that would probably essentially solve the theorem I announced. So that's the existence of higher genus solutions with negative mass. But so now, once you know how to do this for a bretzel, you can just iterate this construction and get higher genus solutions. So for example, this one you can obtain by, you take a torus and you put 2 punctures on it, right? So rather than putting 1 puncture, you put 2 punctures. So you remove 2 points, make a replacement of bihyperbolic space in the neighborhood of this point on this point, and then make a gluing construction like we did with, you have to go to infinity to make sure that everything works out nicely, and or almost to infinity, well, almost to 0 with this factor, and the geometry going to get looks like something like that, right? So that this you can create a connector of the torus with itself across two punctures. Well, here's another one where you have 2 tori, and you put 1, 2, 3, 4 punctures on a single donut, and you repeat the construction, and you get this structure which has what genus? So there's 1, how many holes? 1, 2, 3, 4, 5, 6, right? Genus 6 surface with negative mass if you started with negative mass for Wittmeyer's matrix. Now, the point is that once you realize you can do this, well, first we wanted to construct this example which has negative mass, but then this method allows you to add pieces with negative mass to something which already exists. And so whatever existed before, you add at infinity a Horowitz-Myers metric with negative mass, and you're going to get something which has lower mass, right? So the above construction can be used to lower the total mass of a asymptotically locally hyperbolic manifold with a localized deformation. So the deformation is really first happening near infinity, and second, it's only happening in a small neighborhood of the boundary at infinity. So in other words, everything else remains the same except a small piece at infinity, right? Well, the price is that you're changing the topology of conformal infinity here. So for me, it kind of indicates some kind of instability of these models, and that would be nice to perhaps try to explore, understand this better, right? So, I mean, when you can lower the mass of a physical system by doing something to it, then this means that maybe the system is not stable, right? Also, there are these fancy ideas of space-time forms where you think that in quantum gravity, the topology locally can be fluctuating. And so if you think in terms of these ideas that actually the world is at the boundary of living at the boundary, and you admit this fluctuation of the topology at infinity, then this fluctuation of topology infinity lower your mass, right? So maybe there's some kind of instability there. I don't know how to make this precise, and maybe somebody has some ideas. I'd be very interested to hear about it. Now, one of the conclusions is also that the existing inequalities for mass, and there are a few of them. I already mentioned one by Lee and Neves, that under some condition, the mass of Birmingham-Kotler black hole is bounded from below. Well, these examples show you that that you need some conditions, because you can actually make the mass as negative as you want if you allow these changes at infinity, right? So there are theorems by Lee and Neves. There was a theorem by Gibbons. Greg Galloway and me and colleagues have proved some other theorems like that, where you make various topological assumptions, and these are just plain wrong without further assumptions, right? So one needs those. Let me finish this by two conjectures. One is that if you fix the genus of the conformal boundary at infinity, then there exists a universal lower bound, which would be negative. So if you have a sphere at infinity, a round sphere at infinity, the bound is zero. And if you believe the Horowitz-Myers conjecture, then there'll be a bound given by the mass of the relevant Horowitz-Myers solution. And then it's tempting to conjecture that whatever the topology at infinity, you will get a lower bound. And with our construction, it's clear that this lower bound will be negative, except if you're on a sphere. Another conjecture you could do, well, maybe there is a minimizer for this. Therefore, if this bound is true, then maybe there's a metric which realizes this bound. And of course, the metric would be static. That's kind of a standard arguments now using this various Carlota-Shahn or Corvino-Shahn deformation. Then if you have a minimizer of the mass, then it must be a static metric. So I think that this is all I wanted to say. And so thank you very much for your attention.
Thank you very much. There is time for questions. Somebody would like to ask a question?
Well, I have a question, right? Can someone just this instability, right? So if you have such a situation where you can lower the mass of a solution by something which is happening very far away, how can one understand this, either classically or in a quantum kind of thinking? Anyone has any ideas, suggestions how one could exploit something like that, or to make more precise something like that?
Jurek, it was question to you.
Probably.
I never considered sums with respect to different topologies, but I can see it opens Pandora box for.
I mean, you can think about tunneling, right, between these.
Yes. This is what
what
they say, that then you have tunneling and.
Right. I mean, that's the usual word. Right? When they do this, I think there was a big fuss about it with Young-Mills theory or instantons or something like that, right? When you're tunneling between various instanton topologies or something like that. So.
Yeah,
well,
I think that long time ago, Wutte showed that some higher dimensional, that some Kaluza-Klein theories are not stable. I think it was about even Minkowski spacetime, but maybe in higher dimensions.
Right. So there was this Kaluza-Klein bubbles or something like that, right? So Kaluza-Klein boundary conditions with negative mass, and they had solutions like that in some supergravity theories, right? But then is it clear that this means an instability, or is it just wishful thinking or words, or can one make something out of it?
I have some more technical question. So there is this nice class of, mathematically nice class of generalizations of the Schwarzschild metric, where you introduce cosmological constant and you change topology of spheres into
right. But these are these
genus, arbitrary genus to surfaces. So do you mean that you can construct, you can also apply your gluing to those exact solutions, that you glue two exact solutions and obtain a third exact solution?
Well, so of course I always get exact solutions of the constraints, right? So there's no.
Yes, I understand.
Now the question is, are they explicit? No, of course, right?
No, but I mean those explicit exact.
Yes, well, yeah, of course. I mean, you take two BK solutions and then you can glue them together and you get something which is exactly BK, except for a small neighborhood of where you glued, right? So there'll be a small region. Let me just go back to this slide here. Right. So outside of this blue thing, you had exactly what you started with. After the gluing, when you cross this boundary, you'll get another copy of what you started with, right? So the doubling you can think of is as adding exactly some connector in this red region. But in this region, there will be necessarily a perturbation, right, which is not explicit. So.
Okay, but it means you glue them at infinity, yeah, something which is
near infinity.
Near infinity. Yeah. So. Yeah. It is interesting, of course, for science fiction that we never see infinity, so everything can happen at infinity. Yeah, we can go to another copy of our three-dimensional world.
Well, you can think that lambda negative is science fiction anyway, right? Because observationally, I think lambda is positive today, at least. Maybe we'll change in the future.
Yeah, if you.
Yeah, you can think of interstellar too, and in now this spacecraft would go to infinity, to conformal infinity, rather to the black hole.
Piotr, but I understand that this kind of structure leads to negative mass. It means it cannot be a hypersurface in asymptotically flat space.
Well, it cannot be asymptotically flat because it's lambda negative, right? So to start with, but
okay.
Of course, I was emphasizing the fact that you're gluing two Horowitz-Myers things because I wanted to get something new, which is a higher genus with negative mass. But this construction works for anything, right? So you glue together two positive mass things, you're going to get something which has positive mass, or you're going to glue something which has positive mass and negative mass, it's going to have a lower mass and so forth. So here there is no, this negativity I was emphasizing is just for the sake of the end product. I think there is a interesting question which was realized, which arises here. So the manifolds we are looking at have these punctured manifolds at the limit. But before you go to the limit, everything is compact and smooth, and this formula makes perfect sense. Now you can formally pass in the limit to this in this formula and put as the this static potential, one which arises from a puncture, and therefore this integral still converges. The boundary is not compact anymore because you had to remove a point. So you end up with a formula which is probably, I think, correct for this punctured geometry, but it's not clear whether it's correct because to derive this formula, I assumed that the boundary was compact, right? So to prove that this is the formula for energy, I assume the boundary is compact, everything is smooth and converges at the boundary, and we had this formula. So I think it might be interesting to understand what would be the correct formula if at the infinity you take as infinity your punctured torus or a punctured higher dimensional manifold, whether the punctures will give you some contribution here, right? So it doesn't matter for my proof, because in our proof, we're making claims about the manifold, which is almost the puncture, but not the puncture itself. But I think it's an interesting question. I never thought it might be interesting to look at non-compact boundaries until we realized that this case. So there's some maybe a diploma project or bachelor projects just to try to check whether this is the right formula when you have punctures at infinity, or maybe there is actually a contribution from the punctures to the mass.
So I have a question. Are some at the beginning of your talk you mentioned some applications? Yeah, can you come back to this point? So what would be, say, special application of your result useful for?
Right. So the result says, well, first there exist solutions which have negative mass, which was not known, right, with higher genus, and second, the existing theorems for there are various theorems here in these cases other than canonical spherical under restrictive conditions. For example, the mass aspect function has to be negative here, right? So when we do our construction, there's always a region where the mass aspect function, well, first, it might not even be defined in this gluing region. And second, there is this flat region where the mass aspect function is exactly zero, right? So this theorem, for example, is a beautiful theorem of Lee and Neves here, which assumed this. It wasn't known whether this is a sharp result or not, but now it's clear that some kind of conditions have to be imposed to get the Penrose inequality with negative cosmological constant, because this is essentially what they did, right? They proved a Penrose inequality with negative cosmological constant when the Penrose inequality actually involves a negative mass, right? So there is a negative sign in the Penrose inequality of various terms appearing there. Right. So this is the applications. The first applications we know of, and while we're trying to think about further ones, well, this instabilities, of course, if one can make sense of it, this would be another consequence of what we did.
What about string theorists? As you is any?
I don't know. I don't talk to string theorists. Please stop recording.
Okay, some other questions? What? If not, thank you very much for your talk.
Yeah, thank you very much, and have a a very